Okay, it's now 8 p.m. Welcome everyone. Thank you for linking in this evening as we schedule our monthly EMDRC meeting. I'd like to welcome Steve Adler, VK5 SFA, to our club. First off, and thank you, Steve, for agreeing to present to us this evening. Very much looking forward to hearing everything you've got to say about magnetic loops and the like. I think everyone's well and truly read the website and also the intro in the monthly magazine, so I don't think I need to go into it other than to say Steve's been an enthusiast in the field of amateur radio for many years and has done a significant amount of work in relation to the magnetic loop and related technology. So just a couple of rules of engagement for everyone in case you haven't caught up with it. Steve will run his presentation for however long it takes this evening. You're welcome to ask questions, but I ask that you ask the questions by raising your hand using the Zoom functionality, usually down the bottom of your screen, to stick your hand up, and then Steve will then manage or facilitate the questions. In the interim, while Steve's talking, I ask that you mute your microphone so that we don't have any accidental disruptions like phone calls, news broadcasts, etc., etc. So, without any more time wasting on my part, Steve, good evening and welcome to EMDRC. We're very much looking forward to your presentation this evening. So I'll hand over to you.
Okay, well, thank you very much. Well, hello everybody. Nice to see. Wow, I'm just looking at the admittance wall here. There's an awful lot of people. Look, some of you would know me. I used to be VK3 Bravo X-ray for many years, from about 1976 right through to about 1997. I moved over here. So for those that know me, hello, nice to see you again. So I'm going to be talking to you this evening about my 160 metre and 80 metre transmitting magnetic loop antenna. So there we go. There's a picture of the antenna, and the heading's in red because it really stands out above the green. That's the only difference there. So that's exactly what the antenna looks like. Okay. As I said, conversational styles, green. See, it's good. No death by PowerPoint. I encourage audience participation and ask questions, please. So we'll just quickly blast through this because I've said it all before. You know, do you want to work these bands and you don't have a lot of space? Do you suffer interference? Do you live on a small allotment? If you do, then this antenna could just very well be for you. So then we just touched on what is it. So they're physically small. They're electrically small, very short circumference and far of percentage of wavelength. As I touched on, they've got uniform current distribution. The highest voltage appears across the tuning capacitor, which we'll touch on a bit. They exhibit very narrow bandwidth, which I said before, but that's a very good indicator if you built one properly, because if you haven't built one properly, you won't get that very sharp bandwidth. It's a dead giveaway. Very high Q. They reject a lot or most of electrical noise in the near field. They are bidirectional, so they do behave like a dipole, but slightly opposite, and they make excellent receiving antennas as well. Alrighty, so I think we're getting close to where you picked me up on here. So again, my design criteria was just to build the antenna that radiates a reasonable amount of RF power between 20 and 45 degrees elevation. And that was for DX. I was really looking to this antenna more as a DX antenna. I was very interested in DXing on 160. I'd never really worked the 160 meter band for DXing, certainly for local, but and if it would give me local comms, that would be a bonus. Most importantly, to come up with a design that could be modeled in NEC, just to see how it would behave, then construct the antenna, and then prove the predicted results by going out and measuring them, which I did. And then to publish the design and make sure that you could make it mostly out of basic hand tools and things that you could buy from a hardware store. Okay, so here's my red and green system. So you saw the green before. The red just it just lets you know that these things you've got to pay some attention to. So the antenna is over 3 meters in diameter and weighs about 30 kilos. So it's pretty heavy, a bit unwieldy. It's got to be mounted on a suitable post and guide for stability. In my instance, I've got about 100 kilos of concrete under it and a steel post. Doesn't move. They do exhibit very high voltages and very strong magnetic fields. So you just got to be careful where you put it. And as I said, it's more for people with implantable devices that you've got to be a bit careful here. In actual fact, the distance for public exposure is not very far. Now this is where we got to. So the antenna needs to be rotatable because there are pronounced nulls in the horizontal radiation pattern under about 30 degrees in elevation. So, you know, if you're broadside to the signal that you want, you might not even hear it. So you've got to be able to rotate it without running out there and rotating it. Local ground conductivity will affect the performance, but there are techniques that can be employed to minimize ground losses. So my ground conductivity where I live here is reasonably poor, which is good. These antennas will work best in the Sahara Desert where there's nothing but silica. They don't work as well when the ground conductivity is very good. They tend to get a lot of induction into the ground. And all your connections must be brazed or silver soldered, and we'll get into that in a little while. So I've got to stop here and say I had a couple of mentors here who live in Adelaide that helped me when my initial investigations. One of them was Paul Lawson, VK5 Sierra Lima 5SL. Paul used to be the chief engineer for the ABC and looked after pretty much everything RF, and he is an expert in neck modeling. I am not an expert in neck modeling. He is, so he helped me. And of course, the other person that I must pay a tribute to, of course, is Lee Turner, VK5 Lima Tango or VK5 Kilo Lima Tango, who's a associate professor here in Adelaide, and he deals in magnetics. So he is one of the world authorities on magnetic loops. So he was incredibly helpful, but we'll talk about that a little later.
So sorry, did you see that question from Jeff through TL in relation to the heaviest individual?
Yeah, definitely the actual conductor of the primary loop. It's all copper. So in my case, it was waveguide. We'll get to that. That's the heaviest component. All right. So looking at the drawing here, I don't know how well you can see the colors, but this is just a drawing just showing you the actual current distribution. You can see as it gets towards the top, and this was typically with about 400 watts RMS, or actually I should say 400 watts of carrier power. That's really bad terminology. Not that you would ever do that, but you get up to 50 amps, 50, 60 amps flowing around this. And this is why it's just so important to make sure that you've got really good DC low resistance from a DC point of view. So here is a little model of what the magnetic field looks like. So you can see it under the antenna. And I might say this took Paul about a month to get the shape of this antenna into neck. It's a very unusual shape. It's not a dipole. It's not a vertical. You know, it's not a Yagi. It's a couple of loops that in a solenoid configuration. So you can see it's sort of the magnetic field just follows the plane of the loop, which is standard theory for a magnetic loop. They listen and transmit in the plane, and you can see the nulls off to the broad side underneath. The next slide here is in actual fact the actual radiation pattern of the loop, and you'll see it looks like a giant sort of a mushroom at the top. And as you, okay, I'm going to put my laser pointer on here, which will probably be very helpful because I can point. Right, so you can see here at the near ground level, so very low angle of elevation, there's a null there. And as you get higher and higher, that null tends to disappear. So you'll find for local contacts with this antenna, you know, anywhere around Australia, really, where angles are coming in, you know, 40, 50, 60 degrees, NVIS sort of thing. The antenna is not directional at all. It just receives in any, doesn't matter where you put it, you just receive equally well. When DX is coming in and it's, it's under 40 degrees, you're starting to get into this area here. So it's very, very important that you make sure that null is at 90 degrees to the incoming signal. So, you want to be pointing, this away, if you like, through the antenna. So, and I can assure you this modeling, what it shows really is happening in real life. So there's a plot just of the vertical pattern. So you can see it's just big mushroom, as you can see. Really good power out to 60, starts to fall away as you get lower and lower, and down towards 85 degrees. It's what are we here? It's nearly 10, 15 dB down. So, signals in this area for DX do work quite well. And I found that empirically, which is really good. Paul, just for fun, I had a inverted V for 160. It was a loaded one. So he just modeled it for me just for fun. And we all sort of know that inverted Vs are reasonably omnidirectional and reasonably spherical in their vertical radiation pattern. So he just modeled it as a bit of a comparison, which is quite interesting. And you can see it doesn't listen particularly well until you get up for NVIS propagation, and that all standard theory coming to light here. So that's just a comparison between two antennas, just for reference sake, I guess. Alrighty, so do's and don'ts. Well, no, I say musts and don'ts. When you want to build one of these antennas, you really can only use a non-metallic material as a supporting scaffold. Now, conveniently, I found that PVC high-pressure irrigation pipe and fittings fitted my imagination well. I had an idea of how I wanted to make it. So I got these from a company called Perth Irrigation. They're quite cheap. I got the pipes locally at the local Bunnings, just 90 millimeter, 50 millimeter pipe, and all the fittings came in. They were cheaper. They, in actual fact, to have them sent from Perth, they were cheaper than buying them locally. So that's the actual scaffold just sitting on a little tripod that I have for making things. You must only use copper or aluminium as the loop conductor. At the end of the day, the RF flows around, all the current flows around the conductor no more than 4 or 5 microns underneath the surface of the conductor. So you need a conductor that's non-ferrous and a good conductor. So just important to understand that. Aluminium or copper really are the two good materials for making a magnetic loop. Cross-sectional area is really important if you want to get any sort of efficiency out of this antenna. It really has to be as large as possible. So I ended up scoring some 7 gig waveguide. Just the industry that I used to work in, right place, right time, and a creative beer scored me a whole lot of this. So this is great because there's nothing inside it except air. We have found though that LDF 550 7/8 heliax coax is just as good, just slightly heavier. But I've got many antennas, people that have copied my design, used LDF 550 with tremendous results. So waveguide is very hard to get. So that's just a picture of what the waveguide looks like. Okay, you must use variable capacitors that exhibit low loss. I mean, capacitors have resistance in them as well, believe it or not. They have losses. Variable vacuum capacitors, which are my personal favorite, but butterfly capacitors are ideal. You can use trombone ones. We'll look at a few pictures of those in a moment. But you've got to understand that with 400 watts PEP of input power to that antenna can generate 10 kilovolts across the terminals of where the capacitor is. So using a little close-spaced air one, it'll just arc straight over and it just won't work. So I find variable vacuum capacitors fantastic. They can handle, if you choose the right model, incredibly high voltages. They also have a built-in reduction gear mechanism in the way that they move the bellows back and forward and move the plates back and forward. So bit of a fan of VVCs. You can still get them, still quite a good supply out of Russia. You get a lot of the American ones still on eBay. Unfortunately, when my article got published, which we'll talk about a bit later on, the price of them shot up because everybody went and bought them. So it was a supply and demand thing. Here's a nice picture of a butterfly type. Excellent capacitor for making a magnetic loop, provided the plate spacing is wide enough to give you the right voltage breakdown number. Here's a picture of a magnetic loop with a piston trombone type. Basically, it's just all this is all welded together, so beautiful, very low ohmic resistance. Teflon inserts, and then a couple of pistons on either side, and they make a beautiful capacitor. And it's wound in and out on a screw and thread arrangement. Nothing wrong with that. It works really well. And then there's your old favorite, which you've all probably got a few of, you know, the Hammond type or the like, you know, nice big air spacing and so on and so forth, except they're the wrong capacitor. So these ones have a little commutator at the end here, and you get resistance here, and they do not work particularly well for magnetic loops. Just steer right clear of this type of capacitor where you have a commutator connected to one side of all the plates. They really are just trouble. You'll get arcing, you'll get all sorts of carry on in this area, in this area here where the commutator touches the other set of plates. So do not use these capacitors. You'll just be very, very disappointed. Look, there's other materials that you can make the primary loop out of. By the way, just for clarity here, we're going to call the outside loop the primary loop and the little loop the secondary loop. So when I talk about the primary, it's the big one, and the secondary one is a little one. If you look really carefully, that's a bicycle rim with a capacitor across it. Works fine. Now, I popped this little slide in. These are really popular. You'll see them advertised, commercial type varieties, and there's just one particular design criteria I don't like. Lee Turner, who I would suggest he knows more about this subject than most, doesn't like, and that is they put the tuning capacitor at the bottom, and then they put the actual secondary loop at the top. Now they work, however, the greatest losses in a magnetic loop, transmitting magnetic loop antenna are ground losses. And here you are putting the highest impedance point of the whole antenna right next to the ground. So all you're doing is warming the worms. This is not a good way to do it. Really, the best way to do it is invert it like I did, and you have the tuning mechanism right up the top, right away from ground, and you put the coupling loop, the secondary loop, at the bottom. And of course, forgive my very poor attempt at brazing here, it was my first shot, but silver solder or braze all connections because DC resistance is your absolute enemy. Now you can measure the DC resistance. It's on my antenna, the big one, it comes in at about 0.01 of an ohm, and that's where you need to be to make a transmitting magnetic loop antenna work. So this method of you can't use a multimeter, right? The resistance of the leads of your multimeter is down at that level. So you've got to use this 4-wire Kelvin method, and that's how it's done. And if you look carefully here, you know, we've got about 0.7 of a volt across the antenna terminals and nearly 7 amps flowing. So you do the math and it comes in at about 0.01 of an ohm. So that's how you do it. Very simple method. Really, really good, important check, because, you know, I have many constructors call me most unhappy. They've spent all this time and money and the thing doesn't work. And I've always gone back and talked it through with them. And in most instances, they had a connection that was not good. And of course, it's basically swamps the Q and the antenna doesn't work properly. It doesn't radiate well. And of course, they're unhappy. Another must is for the secondary loop here, do not be tempted and use RG213, 214, RG8, RG8X, forget it. It's not the right. Any braided coaxial cable is no good because it just doesn't give you great skin effect performance because it's braided. You've really got to go with a cable that's solid on the outer. So this particular one's 1/2 inch rigid. It's known as LDF 450. Get a myriad of connectors for them, and they make excellent secondary coupling loops.
Steve, can I just ask on behalf of Tom, radiation efficiency versus transmitter power?
Well, we'll come to that. If I could take that on notice, we'll talk about how efficient they are or not, and that's a whole function of enclosed loop area. So please, if I could take that on notice, we'll get to it. And you can see here, this has just got an enormous amount of solder on it, and then ultimately you have to weatherproof it. So I just used vulcanizing rubber tape, and then a liberal dose of UV stabilized PVC tape on the top of it. And as I said, I haven't touched it in 6 years. So that's a must. You must use a solid conductor. The next thing you need to understand is that this antenna is a balanced antenna. It's not an unbalanced antenna. I've seen many iterations where people have made a TMLA and actually used a gamma match. And all that does is skew the pattern. They're not a symmetrical pattern anymore, and they're unbalanced and they're noisier, and don't do it. The best way here is just to use a secondary loop and then decouple it with a common mode choke with the correct material for the frequency band that you're looking at. So in this particular case, that's I think a type 71, I think. So that's really good down into the hundreds of kilohertz, right up to about 3 megahertz or 4 megahertz. That's excellent material. So, and you can see that that's wound as a split wind. And the reason that you do that, you wind, 8 turns one way and then bring it around, and then 8 odd turns or whatever the other way. And all that does is it stops transformer action. If you wind them all the same way, you start to get RF potentials increasing as you go up the coil. It's just a transformer, remember? Whereas if you wind them this way, that cancels out and gets rid of any of those sort of problems. So you've got to have that just about at the feed point to balance the antenna. You've also got to decouple all your control wires. Remember, you've got a rotator cable going to this thing. You've got another cable going to whatever motor that you're going to use to tune it. So, just decouple it with lots of little ferrites, magnetic materials. And see, just indiscriminately along the way, I had a bit of a problem halfway along the cable. That completely stopped my problem. It was quite effective. As I said before, you've got to try to make the antenna rotatable because there are significant nulls present in the HRP. So as you can see here, there's a little Yaesu 450 rotator underneath it. And I'll just bring that slide back here of the neck modeling. It's this that you're worried about. When you've got those low angles coming in, that is going to sometimes make the difference between you hearing them or not even knowing that they're there, unless you orient the loop in the plane of the direction of the incoming signal. Good waterproofing techniques. So I'll go into this a bit more at length, but I ended up just using a jerry can that I cut the bottom off, a little bit of surgery on it here, and it just sits over my variable vacuum capacitor as a range shroud, if you like. The bottom's completely open, so there's no condensation can ever take place, and as I said, I've had no trouble with it for all these years. Try to mount the antenna at least 2 loop diameters above the ground where possible. Now that is really difficult on 160 meters. The bottom of the antenna really should be here, or even higher, but I just couldn't do it. So mine is a severe compromise here. That point there is about 1.5, 1.6 meters above the ground. But look, at the end of the day, it still works really well. But if you can get them up higher, and I'll show you a gentleman who actually solved that little chestnut in a later slide. And you've got to guy it because, as I said, the wind will blow it around a little bit. So there's all the things that you've got to consider before you make this antenna. Okie dokie. So the design and construction phase. Well, a small magnetic loop antenna is defined as having approximately 1/10 of a wavelength in circumference. So if you read John Krause's excellent antenna handbook, that's what he'll tell you. It equates to about 16 meters of circumference on the 160 meter band, 10%. So using this circumference, the diameter of a single loop, I should say here, would be approximately 5.2 meters. Well, that's an enormous structure that you've got to try and keep still with non-ferrous materials or non-metallic materials, you know, very difficult. And that's what started me thinking about making a solenoid, but we'll get to that in a tick. So I decided it was just too large. And look, I searched the internet, you know, it's a good place for design ideas, and that led me to consider starting to think about a solenoid. So two turns in series, if you like, just a two-turn inductor, really. Using a similar circumference would make it about half the diameter. So I settled on here making 2 loops approximately 3 meters in diameter. And I actually found just by empirical experiment that about 0.15 of a wavelength, and I say 23 meters here, it's not quite 23, but I say that so people just buy the right amount of coax or waveguide or whatever and have a little bit to cut off in the end. I've had too many people, when this was a different number, buy an amount and not have enough. So I found that that is a good sweet spot. As I said before, I used Helix waveguide for the main loop, the primary loop, it's ideal because it's got a solid copper corrugated outer conductor, which is easy to bend. It's protected with a polyethylene sheath, which keeps all the tarnish and weather and things off it, and that's important. Tarnish is not your friend. Tarnish will add resistance and affect skin effects. So it's really good to be able to have an antenna that's not exposed to the air. But unlike coax, it's got nothing inside it, which makes it slightly lighter weight. As I talked a little bit before, I managed to procure some being at the right place at the right time. But please don't let that put you off. LDF 550 7/8 works just fine. So there's a photo of the waveguide that was actually out at the test site. But you can see it's already got a lot of my fittings all threaded on, and you can see some white paint on it because the tower was painted red and white that it came off. So a bit of a giveaway. So as I touched on before, a TMLA needs to be brought into resonance to work. And this is simply done by connecting a capacitor in parallel with the primary loop inductor. I ended up using a Jennings brand. It's a 25 picofarad to 500 picofarad variable vacuum capacitor rated at 15 kV. Now 15 kV theoretically is good for 1.5 kilowatts easily. And that's carrier power, by the way, that's not PEP. So it's got plenty of headroom just to handle 400 watts PEP that we're allowed here in Australia. If you wanted to make the antenna with a single turn, you'd need a capacitor that's probably exceeding 1,000 picofarad. You remember the old formula, you know, double your turns, quadruple your inductance, therefore you only need 1/4 of the capacitance to bring it into resonance. And that's another endearing point using a 2-turn loop. You don't need such a big capacitor. So there's a good close-up picture of said machine. You can see over here, you can't quite see, that's got 15,000 volts written there, 25 to 500 puff, and nice and shiny on the inside because it's all enveloped in a vacuum. Righto, if I can get my mouse back. Come on, mouse. There's a picture of my tuning mechanism. So I have, there's a video of it later, I have made this automatic tune, but to begin with, and this one to this very day is still a very simple tuning method. That's a 12-volt DC motor. So it means it can be driven one way or the other. And then coupled to the front of that's got a little gearbox. And that one's rated at 10 revolutions per minute at 12 volts, which is about the granularity you need. And I'll show you in a minute how on earth we get that to turn even slower. There's a view from the other end. And that's just mounted on a piece of nylon breadboard. Pardon me. Very homebrew, but as I said, it was a bit of an experiment. Very importantly, though, the capacitor is hot with RF. You've got to be able to decouple it or disconnect it from anything else that you're working with. So this actually came with the capacitor. That's a ceramic decoupling mechanism. So it transmits mechanical rotational forces through it, but it isolates it electrically, if that makes sense. You can do the same thing with just a piece of fiberglass, solid fiberglass rod works just as well, but that came with the machine, so why not use it? To power it, a very cheap and cheerful but excellent little design. This is a little pulse width modulated DC power supply. So it's got a forward and reversing switch on it. It's got a speed control on off speed control potentiometer here. And it works really, really well, as you're about to see on the next slide. All right, so I'll just turn off my laser pointer so I can make this work. So the setup, actually, I'll just show you, put it back on again. The setup here is my hand, the little pulse width modulated DC reversible power supply, the DC motor, and the capacitor. And this is just a simple digital multimeter, but with a capacity function. So that's measuring the bellows set. These are the bellows, by the way, and the actual plates set at about 0.295, 295 picofarad. So this is actually a video. So you'll see I started off at high speed. I'll slow it down, and the rate that you need to tune this on the 160 meter band is a rate of tuning of about 1 picofarad per second. So that's about the magic number. When you start to go into stepper motors, that's a whole different ball game. So here we go. So you can see it's spinning away. You can see the capacitance dropping. I speed it right up. You can see it's moving quite quickly. I slow it down, and you'll see we get to this magic 1 puff per second, roughly. Reverse the switch. Spins the other way, and the capacitance starts coming up quickly. So you use that to get from one end of the 160 meter band to the 80 meter band, and then when you get close into where you want to be, you just slow it down and stop it.
Steve,
really simple.
Steve, there's a question from Graham XGA. Would a 3 or 4 turn loop solenoid design still work?
That's a fantastic question there, Graham, and thank you for asking it. The answer is no. Now, 2 turns is the limit. You start to go to 3 and 4 turns, and you get these incredibly complex phase issues where the signal cancels out within the antenna. 2 turns is it. You can look, 3s will just sort of work. You'll be really disappointed. One turn or 2 turns, that's it. Just how it rolls. Okay, so there's a mechanical layout, not to scale, but you can see, each one of these arms is about 1500 millimeters every which way. One of the critical distances is the distance between the 2 loops. It's about 300 millimeters or around 600 across, roughly. You start to go larger than that, you can get some very interesting problems where the VRP, the vertical radiation pattern, will start to fire into the dirt. And it won't work well, and you won't know why. Similarly, if you get too close, it can do similar things. So that, again, was just found with empirical experimentation to get the best field strength. And that seems to be about the number. Okay, doke. So there was the scaffolding, just to refresh our memory, sort of what it looks like a little more close up. These are the spreader arms. Now you'll see here, one arm's got a nice big stiff piece of wood down the center of it. I just found that it was just not stiff enough to support the weight of the antenna. So that piece of wood just fitted perfectly inside, and that goes from the rotator end. I'll put my pointer back on here. So that's where the rotator would be, and where the middle of the antenna is, and it just extends a bit beyond. And that stiffened it up really nicely, and all those problems went away. And of course, wood being wood, it's invisible to the RF. Okay, There's a picture of the scaffold on the ground. This, by the way, these photos were taken out in a local park where we did some measurements on the antenna. There you can see the piece of wood firmly inside the PVC pipe. So that was my test fitment day. You can see my waveguide just to see if it all fitted. See, I've got so much overhang here. You need that because you've got to bend it around to get it back into the capacitor. So that's why I say to people, get about 23 meters of material, because you've got to take that into account. Some homebrew devices just to keep the antenna centered. So I just used T-pieces, but I got some end caps and just pretty much bored a 40 millimeter hole in them, and the waveguide just sat in that. It was quite effective. Mounting the variable vacuum capacitor to the system. So this wasn't brazed up yet. I was just used all brass and copper components. Now you'll see I've just used nice wide 2.5-inch copper strap. That's 1/2 mil copper strap. Everything's got to be nice and wide because it's all to do with skin effect at the end of the day. I've seen people make the classic mistake where they'll just get a bit of wire and connect it from here to the capacitor, and it just does not work. It spoils the cue and the thing doesn't radiate and everybody's unhappy. So nice big flat strap, nice big fat conductors. That's what you want to get the current into the antenna to get the efficiency out of it. I call this one a little bit of copper origami. Just a matter of being able to get it through 90 degrees to get to the other end of the inductor. A good shot of it there with the motor mounted on it. Again, just bolted in place for fitment, and then ultimately I brazed it all up. And then waterproofed it. So again, just self-amalgamating rubber tape, and then a liberal dose of PVC tape, and it keeps the weather off it and keeps it nice and shiny, so there's no tarnish. Just another picture of the secondary loop we've seen before. Again, how I soldered it and how I weatherproofed it. All right, so here comes the fun. So I got it all finished and set it up in my bottom of my backyard. And the first thing I'm going to tell you is my XYL absolutely hated it. She's pretty forgiving in what I do, but she did not like that antenna one little bit, and made her thoughts known very clearly. So it looked like it was going to be an experiment that would unfortunately get packed up and just get experience from it. So anyway, that was the test position. We'll go, but I guess the most important point to make here, if you have a really careful look at the secondary loop here, can you see how it's actually quite small? Now, I made a mistake. If you read the theory books, they'll tell you that your secondary loop should be about 1/5 of the diameter of your primary loop. So I made myself a 3-meter antenna, and I thought, oh yeah, 1/5 of 3 meters, roughly 600 millimeters, say. So I made a 600 millimeter loop, and I put it in, and I measured it, and I got a return loss of 6 dB. So in SWR terms, that's 3 to 1. And I was particularly unhappy about that. So I remember ringing Lee Turner, 5KLT, crying on his shoulder, and like any good engineer, he started asking me a few questions, and he wanted to know what the size of my secondary loop was. And I said, oh, it's 600 mil. And he said, well, hang on a minute. He said, how did you get that number? And I said, oh, it's a 3-meter antenna. He said, no. As a single turn, it's about a 5.2, 5.3 meter antenna. So really your secondary loop needs to be 1/5 of that number, not this compressed number. Oh, wait, you got to be kidding me. He said, no. So I went away and very quickly constructed a 900 millimeter loop. And at that point, I was blessed. Actually, I made it slightly bigger. It was about 1,000 mils to start with, about a meter in diameter. Anyway, I ended up at 900 millimeters because I got a VSWR here of about 1.3 to 1 on 160 meters, and I optimized it to get about the same 1.3 to 1 on 80 meters, because that was the other thing that I didn't know. That was really quite a surprise. I didn't know this antenna would work 1 octave above its design frequency. So getting 80 meters as well was just the most incredible bonus. And we'll talk about efficiencies. Might just talk about efficiencies here at this point. So I optimized my secondary loop to give me that 1 octave of coverage. So the antenna, in actual fact, it'll resonate from about 1.45 megahertz in the AM broadcast band, and it goes all the way through to about 4.2 megahertz in the shortwave band. So any frequency in between those 2 points, it will resonate. But more importantly, inside the 160 and 80 meter diameter bands, I get about a 1.3 to 1 or better VSWR. So someone, I think Tom it was before, just asked me about efficiencies and so on and so forth. So on 160 meters, the efficiency of this antenna is 5%. So in real terms, that means you put 100 watts of carrier power into that antenna, and it will radiate 5 watts of that power. That's because of its inefficiencies, because of the enclosed loop area. Now, the most important thing to understand is, whilst it's only 5 watts, that 5 watts is being pointed down towards the horizon. Now, there is no way known on a quarter-acre block or smaller in suburbia that you are going to create an antenna that's going to do that. I don't care what you make. Even if you do a vertical, your ground system is going to be so poor, its efficiency will be just as bad. So, and it'll be as noisy as all get up. If you do a horizontal dipole, well, you know, what's the maximum height you're going to get that 160 meter dipole above the ground? 15 meters, maybe? Well, that's just going to shoot straight up. It's just be NVIS, great NVIS antenna, but no good for DX. So it's just important to know, whilst the efficiency is down, it does put usable power down on that vertical angle. So keep that in mind. On 80 meters, however, it's a whole nother story. That antenna starts to become about 82, 83% efficient. Now, when we talk about efficiency, what do we reference that to? Well, that efficiency is referenced to a horizontal half-wave dipole half wavelength above the ground. So if we had an 80 meter half-wave dipole 40 meters above the ground and compared it to this antenna would have about 14–15% less efficiency. So it's extraordinary. This thing is an absolute weapon on 80 meters, and I'm going to demonstrate that to you a little bit later on. So 5% on 160, about 80% on 80. So here it's all packed up, ready to take it to our test range. So managed to load it into my friend's got a small flatbed truck, so we popped it all in there. Went out to my local park here and set it all up, and I'll talk through the test procedure in a minute, but you can see it's now sporting its really nice big secondary loop here, and of course the primary loops, as we've seen how I built it. Not very high off the ground, to be honest, but again, this was a portable sort of a situation. Okay, so how do you measure such a thing? Well, I'll go forward one. So this apparatus here, by the way, that's Paul Lawson VK5SL. And that thing there is called a field intensity meter. It's made by a company called Potomac Industries, used extensively in medium wave broadcasting, short wave broadcasting, and it measures field strength, absolute field strength. It's got a little magnetic loop built into the lid here, and it's got a meter, and you can null it out and you can get straight on into the loop, and it'll give you a field strength measurement in volts, which is pretty handy. So my idea, because I wanted to measure the vertical takeoff angle as well as the horizontal angle, was to mount that antenna, mount the meter on a rope. You can see there's a piece of plastic conduit behind it as a non-metallic staying device, with a couple of ropes so that we could keep it nice and steady. I'll just go back one slide. It'll make probably more sense here if I can get my mouse back. Sorry, folks, let me just put that here. So we installed a sky hook up on top of a limb of a gum tree there, attached the meter to that sky hook, and lifted the field strength meter straight up off the ground. Now, you can see the antenna under test in the distance. So all I did was set everything as at the equilateral triangle, and that would then allow me to measure up to 45 degrees. Well, that's what I thought. I thought it was really smart. And people said, well, how on earth are you going to read the meter? And I said, let's just get a pair of binoculars. And they thought, oh, that's a pretty good idea. So we set this whole rig up, as you can see, and it didn't read a thing, nothing, zip, no field strength whatsoever. No matter what attenuation setting you put onto the meter, it received nothing. And after a little bit of head scratching, we quickly worked out why. And that's because in the near field of this antenna, which we were well and truly within, it's the component of the wave is only magnetic. It's not electrostatic. And this meter needs an electrostatic, an EM wave to actually work. So there was no electrical component. When we got out to the far field, which was about 450 meters away, and that was an interesting effect because it should have been closer in, but both Lee and Paul felt that making a solenoid tended to compress that magnetic field a bit and push it out further. But once you get out into the far field, it reads just fine. So at least we could measure the horizontal radiation pattern and the null. So that was a very interesting exercise, I have to say. Paul just wanted me to put a ground screen underneath it, just to decouple the whole antenna from the ground. So there's just some little radials trying to do such a thing. It really made no difference. There's just a picture of the antenna in situ. Alrighty, so here's a couple of little videos now, just to show you the actual bandwidth of the antenna. I'll try and set this up for you. So this is on my old IC 7700 at the time. I don't own that radio anymore, but we'll run the video a few times and we'll just look at VSWR versus frequency, and you'll be able to see how sharp this thing is. So let's just run it once and I'll try and describe what's going on here. So at the moment, you can see that the needle is set at about, let me see here, I think it's about 3 to 1 from memory. And the scale, if you look carefully here, sorry, I just get my laser pointer going again here. There's 3, there's 2, 1.5, and 1. So it's this bottom scale here that we're interested in. So here we go. So let's run the video. So you'll see the frequency, it's resonance, and then coming back out of resonance. So let's just start the video again. So it starts off at about 1.57 and ends at about 1.857 and ends at 1.862. Watch it again. And you can see how enormously sharp it is on the 160 meter band. So that's quite a good demo. I'm going to give you a much better demo of that a little later on. Okay, so this little video is just showing you the tuning speed of the actual capacitor and the DC motor at full tilt. So you'll just see this is a scale here. If you look on the on here, 1.8 megs here to 2 megs. So it'll just show you the speed at which the antenna tunes across the 160 meter band. So just watch this video. Here we go. Comes into resonance, you can see the noise come up and then comes off and you see the noise die away, and you can see in the waterfall the actual resonant point moving along. So yeah, you can see it moves reasonably quickly. It's probably not the fastest thing in the world, but that gives you some idea of how fast it actually tunes. Okay, well, there's a picture you've seen before at the start of the presentation. Just excuse me a moment. Okay. I had to add a piece at the top here to guide it from the top. Just guying it on 2 axes was, sorry, on 2 directions wasn't enough, so I had to go with 4. We do get some very high winds where I live up here in the Adelaide foothills. Here's a good video of the actual rotation of the antenna. So it was a lovely autumn day from my memory. You can see the speed in which you can physically rotate it. also gives you a good perspective from all angles of what it actually looks like. Okay. Just the waterproofing system, I said, quite effective. I mean, you've seen a photo of that before. Just to keep all the cables centered, I just used some really heavy duty cable ties just to hold it in place. There was nothing particularly fancy. So this next slide is just a comparison. At that time, I had my inverted V on 160 meters, albeit a loaded antenna, and it was during the day. It's very noisy. Lot of rooftop systems. A lot of ADSL stuff going on here, and you can just see a lot of noise across the band. And the meter was reading just on 5 dB over 9 of noise. And there is just switching to the magnetic loop, and you can see it's dropped. So 5 dB, say 11, 17, another 6 dB is about 23. So now 24, 25 dB. Extraordinary. It's a very, very low noise antenna, and I'll give you a good real demonstration of that a little later on. So results. Well, that's a big red sign. We all spend all this money. We put all our hard work into it, blood, sweat, and tears. We want results. We want to know if this thing's going to work. So this is just about accurate. I think I've worked 45 countries now. I haven't updated this lately, but all over the world on the 160 meter band. Very little SSB, quite a lot of CW, and a lot of FT8. To be truthful, they're the two currencies of the day when you're looking for DX on 160. So quite a good performer from a backyard, from a 3 meter antenna with not one ground radial in sight. It's quite extraordinary. This slide was my first ever DX contact on this antenna, and that was into Lithuania, LY7M. And I kept it because that was a bit of a memento. I couldn't believe it. It was in middle of February. By the way, February, March, your DX months for Europe on 160, by the way. And it was we were quite into sunlight at that point, but the rest of the path was in darkness. So that was very pleasing. Just a good night on 160. So into the US, out here to I think where that was, up into Japan, Philippines, really quite good. Probably one of my prized contacts, the VK0EK DXpedition down there to Heard Island. I worked in without any problems whatsoever. It's just a piece of cake on CW. So that was a nice rare one, that one. There's just a little bit of a interesting map just showing you where I've worked on that antenna. So really quite extraordinary if you think about it. So that was on 160. On 80 meters, oh man, it's just another story. It just goes everywhere. Really quite phenomenal. Here's a slide on a good night on 80 meters using FT8. That's 9 minutes of transmission, lit up a lot of the northern hemisphere on the dark facing side of the planet, up here into Alaska, Vladivostok, Japan's, bit of Australia, enormous amounts of the US coming into their dawn. So it works like a beauty. And for those who would wonder what sort of SNR I was getting, I mean, have a look at this. It's +2s, -5s, up into Europe, -13s of good ones, 22s a bit weak, 18s, 19s. Excellent for such a tiny little antenna. Now, I don't know how well this is going to work. This was an audio grab. I just couldn't help recording this. This was a HG8DX, which is a bit of a serious station in Hungary, And he was over S9 on SSB. I don't know how well this will work. We'll see if you can hear it. Let's play it again. That was on 160 phone. Okay, some other people have had a crack at this. This one is not a copy of my antenna. I've got a very good friend of mine who lives up in the Adelaide foothills. Sorry, the Adelaide Hills on a farm. He built a 2-turn again using LDF 550. And he used a current transformer to feed his one. But the reason I put the slide up here is just the way that he can manually change the orientation of the loop. If you look carefully here, let's get my pointer going, you'll just see a couple of gate hinges here. So this whole thing is on a hinge and the antenna is mounted to that structure, and then he can just move that structure through 180 degrees so he can get directivity out of it that way. Just, it's an idea, and that's why I sort of put it up. A very dear friend of mine, Steve, VK7 Oscar. You might have heard him before, excuse me. He built exactly my design, but he just used 1/2-inch coax, and it actually works okay. So, you know, if you weight's a consideration and you don't want to spend the money on LDF 550, 1/2-inch actually will work. He's got a postage stamp of a backyard here. I mean, if you look, here's the back of his house, and there's his fence. There's a ladder for scale, and that man works the world on 160 and 80. I think he's moved since, but it certainly got him onto the low bands quite easily. VK1KF, his iteration, really nice job. Good carpenter, and he's had a lot of fun with that antenna. Another shot of the front of his house. He got it up nice and high. He read my article and did a really good job. Kamal, 4S7AB, maybe a slightly more agricultural way of doing it, but he did it and had tremendous success. He made the mistake in the first instance, though, of not fitting a common mode choke at the feed point of the secondary loop, and the antenna did not work at all. The feed line became the antenna. Anyway, ultimately he bought the correct toroidal ring and made up his common mode choke, and I think he surpassed 50 DXCC in a week. Sri Lanka is a really good place for 160 meters. This next copy of mine, probably one of the best iterations I've ever seen, KO2F in North Carolina. So, you know, he put up the serious frame, mounted the holding in the frame. There's no guy ropes, no nothing. And he tells me he has a lot of fun with that antenna. He just took my design and made it to the next level, in my opinion. Just a beautiful, beautiful job. Just for interest sake, to date, there are about 35 of these antennas that I know of. And there's quite a few people making the 60 meter, 40 meter, 30 meter version of it, and having quite a lot of fun. But there's about 35 or 36 of the big ones that I know of around the world. And the really pleasing part is that everybody that built one comes back and says to me, yep, it behaves exactly as you described it. And I'm really, really happy, and I'm pleased I built it. So that's very pleasing to me. There's one I was playing with. That's a little 40, 30 meter one that I used for going out into parks and things. It's just bizarre. You just sit there with this tiny little antenna and talk to Australia on 40 meters. Just great. Sorry, I just got to get my mouse back. It just plays up when I got the pointer going. So just for fun, I thought, well, how well will this scale? It works on 30 and 40 and 60 meters and works on 160 and 80 meters. I wonder if it'll work on 6 meters. So what you're looking at there is a scale model for 50 megahertz. So it's a double turn, exactly the same design. It's 200 millimeters across. And does that thing ever work? It's extraordinary. I can work DX on that thing if the band's open without any problems at all. And it'll handle 400 watts PEP. It's got a 50 picofarad little variable vacuum cap up the top there. So I just built it for fun. It's got no practical use, really. Just prove that you can do it. So then came the next part of the project. Well, it's all fine to manually tune these things. I wonder if it could be automated. So I built a 60/40/30 version of this antenna, and in anticipation of us getting access to the 60 metre band, which never happened, which was a true disappointment to many, I'm sure. But it does work superbly well on 40 and 30. So a lot of those have been built around the world. This one I used a stepper motor to drive the variable vacuum capacitor. You can see here it's a tiny little one. It's a 5 to 100 picofarad job, rated at about 15 kV. What we've got here now, I am not a software developer. I can write a little bit of code. I'm not very good at it, but I, at the time, was working with a young chap who was working with me, who was not an amateur, but was most interested in helping me automate it. So he wrote some code to make a one-way tuning mechanism, a bit like a step IR or an ultra beam, where you calibrate the antenna. You know how many steps it takes to get to a certain resonance point, and you put that into memory, and then getting frequency information back from the radio, you can drive the stepper motor to that point. So I've since dropped this project because there's one thing that I didn't understand at the time, and that is that variable vacuum capacitors have inherent backlash in them, so that they don't necessarily tune at the same stepping point every time, and that's a function of the worm gear inside it and temperature. I since built another controller which does have that compensation built into it, and it does work quite well. But anyway, what I will do is I'll set this up and I'll show you this video. It was a big learning nonetheless. So what we're looking at here, VSW. Today I'll get my pointer going again here. Sorry. So what we have here is a VSWR bridge, a little IC706. That's just a Windows Surface PC. That's just a web, just a browser looking at the Raspberry Pi web engine in it. So with the program running, so you can see that's the frequency, which is the same as the frequency on the radio. It tells you here the number of steps that it's counting forward and the like. So we'll watch it in operation. I'm changing frequency by using the up and down buttons on the microphone, so that's out of the camera shot. I'm not twisting the VFO here. So, but you'll see a change frequency. You'll see the VSWR go to infinity, and then as the software sees what frequency it goes to, it dials in the correct amount of steps, and the VSWR drops to nothing. So, without further ado, let's get my mouse back again. Let's look at that. So here we go. So you can see the VSWR, as I change frequency, starts to go very high and then instantly just comes back down to resonance. Infinity, back down to resonance. It's really quite cool. So I guess the lesson out of all of this was you can actually automate them, but temperature and backlash do play a very significant factor in repeatability. So that was the learning for me. Yeah, it's all just about having fun at the end of the day. And my young programmer learned a lot about RF, and he walked away with something too. But he did all the code. So there we go. It's quite a good little thing. Anyway, moving along, we're nearly at the end here, and then I'll give you some practical things to quickly look at. So yeah, in 2018, the ARRL have a yearly antenna design competition. This year, that particular year, it was had to be for one or more bands between 2,200 meters and 10 meters, and it had to fit into a very small area. And my antenna fitted the criteria, so I had a good friend of mine encourage me to enter it. In the United States, they don't tend to give this award out to non-US amateurs very often. However, this particular case, I got an email in October of that year, and I'd won first place. Very chuffed about that. It was just amazing, and they printed the article into QST, and that was really good because it got the design out there, and that's when I started getting lots of people writing to me wanting information on how to build it, and that's why there are so many in circulation. So that's pretty much it for the presentation.
Thanks very much, Steve, for your time this evening. Very generous of you to give it up for us. And,
my pleasure.
Very pleased to see that we've had a pretty good turn up tonight as well. That no doubt have enjoyed your presentation and might be tempted to jump on board.